Let's look at a very elegant story connecting geometry to algebra. And this is a good preparation if you're about to think about the cross product, but it's totally stands alone in 2 dimensions, whereas the cross product takes us these ideas into 3 dimensions. So we're looking for the area of a parallelogram. This is something that, of course, we do in a basic geometry class, but not usually, or never pretty much, in terms of vector terminology. And so specifically, we're in the world where everything is described by a vector, and specifically that we've got 2 vectors that are given in components. So V here is AB in the picture. It's going to be 4, 1 for the example that we'll do. And W is CD. That's going to be 2, 3 in this example. And as always, when we put 2 vectors tail to tail, they naturally form a parallelogram. Just slide V up, slide W over. This would be what we draw, for example, if we were going to add V and W. It's just a long diagonal there. We're not going to actually, well, we're going to do that just once, and that's not our main concern, but it's such a natural thing to do with vectors. Conversely, if you have a parallelogram and vectors are your tool for drawing things and understanding stuff, this is a natural way to think about it. The parallelogram formed by 2 vectors. So here's the thing. Of course, we know a very standard formula for the area of a parallelogram, height times base. But that's a little awkward here because it seems to be that we would say, let's think of like V as the base, this tilted base for the parallelogram, and then the height would be the length of dropping an altitude from the tip of W to V. We could totally do that. We have tools for that. But there's actually a really clever, better way, and that exploits the fundamental properties of area in a better way than doing that kind of geometry. Of course, it gives the same answer, and that's going to be cool, but I want to sort of lead you through this better way. So the first clue that there might be a better way is that dropping an altitude from the tip of W to V, okay, dropping altitude is a great idea. Any geometry problem, the moral is usually, the first step is usually draw more stuff. But you know what? The way the vectors were given is in components. And that's a big hint as to a better way to draw more stuff in this situation. Because it's in components, we should drop perpendiculars to the axes. And my hint here is draw a lot of stuff that's either vertical or horizontal. So another way to say it is draw any horizontal or vertical segment that seems reasonable in this picture. Okay, so I would pause the video and recreate that picture, just sketch it out real quick, and see if there's some horizontal and vertical segments that start drawing other shapes that maybe the areas aren't too hard to calculate for. So that's my advice, is to pause on that one and try it out a little bit. Okay, so let's see what happens if we do that. Here's the segments I'm thinking of, and that is to take the tip of W and connect it to the x-axis, and the tip of V and connect it to the x-axis, and the 4th corner of the parallelogram, which is the tip of V plus W, which is going to be important to us, and connect that to the axes. And then, while we're at it, realize that we've basically got some triangles and rectangles drawn. If we just draw this line here, this segment up to that point that's called J, and this segment over to I, what we've got is a picture with one very big rectangle. We're going to see if we can figure out the area of that. I bet we can. And then the rest of it, except for the parallelogram, this complicated guy that we were thinking might be hard to get the area for, everything else in the picture is either a rectangle or a triangle, a right triangle, with sides along or parallel to axes. That's really good. The main thing here is that since the information was in components, we really prefer vertical and horizontal segments. Okay, so you might want to pause right now and think about, where does this go? How would this let us get the area of P? But I'm going to give you more hints. Okay. The main thing, the last fundamental principle, besides when components are given privilege the axes, privilege vertical and horizontal segments, is such an incredibly important principle of areas, also volumes, lengths, anything, an amount or masses, anything that's an amount, and that is the whole is the sum of its parts, right? There's this saying that sometimes the whole is not the sum of its parts. That saying exists because it's so commonly true that the whole is the sum of its parts. And in a situation where you're just counting areas, that's absolutely true. Okay, so this is where we're going to be pausing for real and answering some questions. Is there a simple whole here? And the answer is, of course, it's the big rectangle. And we're going to be able to find the area of that in general for any A, B, C, and D. Are its parts besides P easy to find the areas of? Well, the parts are rectangles or right triangles with side lengths that we can totally get because they're vertical or horizontal. So yes. Easy rectangles and right triangles. Groovy. Okay, so let's do that. Oh, and then, yeah, so let's do that. And then let's see if the whole is the sum of its parts principle can be used to find one of the parts given the whole and all the other parts. Okay. And then here's a cute little thing. You could do it just based on those hints. But there's a very cute little thing, which is I claim that some of these other parts between the R1, R2, T1, T2, T3, T4 can be combined to make it even easier. So you actually don't need to know the formula for the area of anything but a rectangle. Okay. And that's because if you look, T1 plus T2, if you slide those together, that's a rectangle. And it's a rectangle that's very easy to figure out. Yeah, definitely don't want math mode there. That's very easy to figure out the area for. And similarly, T3 plus T4. So you don't have to observe that, but it's very cute. You don't even have to know the formula for the area of a triangle to do this. And that's actually really nice. It tells you that this is really getting down to the very basics. The only area you need to know is the area for a rectangle. So that's telling us this is a pretty clever thing. Okay, so let's look at it. Okay, so I'll do the formulas and the numerical values for this particular situation. The whole, this is the one place we use the fact that going from the bottom left corner, it's labeled A here, capital A, up to the top right corner, is the sum of the vectors A, B, and C, D. And so the x-coordinate of D is going to be A plus C. The y-coordinate of D, this point capital D, is going to be B plus D, little b plus little d. And so it's going, in this example, it's going to be 6, 4. And so in general, the area is going to be the quantity A plus C times the quantity B plus D. In the specific case here, it's 24. Okay, now let's look at the other rectangles. R1, okay, so one of the lengths, the horizontal, is just exactly how much W went to the right, that's C. The vertical here, we have to realize, okay, that's how much this arrow, the top edge of the parallelogram, goes up. Remember, the top edge of the parallelogram, that's just a copy of V. So how much does that go up? That's just going to be B. In this case, it's 1. But always it's going to be B. And so we can get the area of this rectangle. That's just going to be B times C. Very similar for R2. Doesn't it look like R1 and R2 look exactly the same? Why don't you think about that? Let's see if you can get the area for that one. When you combine T1 and T2, remember that's the rectangle that if we actually filled in this point at 2, 0, we would just get the T1 plus T2 combination rectangle. See if you can figure out in general, or just for these numbers, but I'm looking for in general, in terms of A, B, C, and D, what the area of that rectangle is. What's given, which of those 4 letters A, B, C, and D is given the height, which is giving the width. And then the last thing is going to be the T3 plus T4 combination. If you slide T4 down, it's going to be a rectangle just like this. What are the sides of that rectangle? Okay, so hopefully you've paused and done that. And what we get is that R1 is BC, R2 is also BC. In this case, that's 2 and 2. T1 plus T2 turns out to be C times D. And T3 plus T4 turns out to be A times B, 6 times 4. Okay. Now, in this case, the number is just 24 minus 2 minus 2 minus 6 minus 4, and that turns out to be 10. But let's go ahead and get the actual formula for the area. We're just going to take the quantity times the quantity here, subtract off 2 BCs. Remember, there's two, those R1 and R2. The combined triangles 1 and 2, the combined triangles 3 and 4. We just expand this out. Very easy little calculation. And you get a bunch of cancellations. So I want to make a point here. As soon as we did this, as soon as we saw this picture, we're guaranteed to get some sort of formula based on A, B, C, and D that is purely algebraic, no cosines, no sines, no square roots even, for the area of this parallelogram. I think surprisingly simple already. If you thought you had to do like trig and drop perpendiculars and magnitudes or components or projections, things like that. Those often involve at least square roots and often trigonometric functions. So already we know that there's going to be something that's just pure like multiplication and addition and subtraction that's getting this answer. And then it's gravy that in fact when we do it, you don't get something that's this complicated or this complicated. It boils down to a very simple calculation that only takes each letter once, each of these 4 variables once. It's just AD minus BC, and then we get 10.